Welcome everybody to today's seminar. Today's speaker is Monique Teillaud, and she will talk about triangulations, CGAL, and hyperbolic surfaces. Please take it away.
So thank you, Hanka. Thanks to the organizers for the kind invitation. So I start with very trivial stuff, like recalling what a Delaunay triangulation is. I guess you don't need it, but okay. So you have a set of points in some space. Here it's Euclidean, and it's a triangulation of the convex hull, such that all circumscribing disks to triangles are empty. They don't contain any other point in the set of points P, and the dual is a Voronoi diagram. So it has many applications, especially in 2D and 3D, but also in higher dimensions. But so I'm not going to go into those details, but it really has many applications. And in particular, it has applications if you implement the computation of triangulations. So I am going to talk a bit about CGAL, the Computational Geometry Algorithms Library. It's an open source project, and it's distributed under a dual license, both GPL, free, and commercial. So I also won't go into the technical details of C++, but so it's a C++ library, and we achieve genericity and flexibility using templated classes. I'll show a picture with an examples, but I won't go into technical details. So there are many chapters, many packages in CGAL, and I will only focus on a few triangulation packages, but there are many other things. So in particular, what we've been working on are triangulations. And so you have Euclidean triangulations, 2D, 3D, higher dimension as well. But also triangulations, what we call periodic triangulations is actually triangulations of the flat torus. And it's really restricted to a square or a cubic domain in 3D. Nothing more. We have hyperbolic triangulations in 2D, and hyperbolic periodic triangulations are triangulations of the Bolzan surface. So again, it's a very specific surface, and I will tell more about that later. And we also have triangulations on the sphere. So I will spend more time on those in pink, but I start with the easy ones, the Euclidean ones. So just to get here, it's a slide to show that it's easy to use. So this is the only thing that I had to do. I'm not very good at installing software and things like that. And but so to install CGAL demos, compile and run them, you only have to do those this small list of operations. So it's easy. That's the only message I want you to remember, that it's easy to use. So the general design for Euclidean, at least, triangulations. So you have a class that computes triangulations. So here it's a triangulation D, and it has two template parameters. So the first one is what we call the geometric traits, and the second one is the triangulation data structure. So the first one is in charge of providing the triangulation class with elementary objects and elementary operations. So elementary objects like points for the case of triangulations. And the elementary operations are either predicates, so compute whether a point is in a circle or not, for instance, and constructions could be like, for a Voronoi diagram, compute a circumcenter. So that's basically what the traits is supposed to do. And the triangulation data structure gives the combinatorics. So in 2D, 3D, it stores actually only the higher dimensional simplices, like triangles in 2D or tetrahedra in 3D. And so they are the simplices, and you only store pointers to their vertices and pointers to the adjacent cells. And you also have vertices for which you only store one incident cell. And then, so that's all for the combinatorics. And then there is communication between those two classes, and the vertex stores a point that is given an object of the type given by the geometric traits. So that's basically the data structure and the organization of who is doing what. Now I go to algorithms. So again, it's quite trivial, but still to make ideas clear. So I focus on incremental algorithms because these are the ones that we code because these are the ones that are more practical. So there are two main classes. I start with the first one, Boyer's algorithm. So it constructs a Delaunay triangulation incrementally. So you have a triangulation, you want to add, insert one point. So the first operation is to find all the simplices whose disk or ball in higher dimension contains the new point. These must disappear. So you have a region that I call the conflict region. It's the union of such triangles. And it has the properties that it is a topological disk or ball. And then the only operation that is needed is to create new simplices having the new vertex, the new point as a vertex. And so if you look at the global picture for the CGAL organization, finding the simplices in conflict is pure elementary geometric operations. So you need to check whether the point belongs to a circle, a disk. And then you have the creation of the new simplices. It's purely combinatorial. So you have a clear separation of the roles of the two template parameters. One helps computing the predicates, and the other one is used to update the combinatorics. So we like it in CGAL because it's clean, because of this separation, clear separation, and it allows for efficient implementations. The other class of algorithms is Lawson's flip algorithm. So of course, the result will be the same because the Delaunay triangulation is well defined, but the organization of the operations is different. So the first operation is to find the point, the triangle that contains the new point. You split into three, like this, like in the picture. And then for each new edge, you check whether it is Delaunay or not. So on this picture, you check first this edge here. In this case, it is not Delaunay, so you flip it. You do the same with the other edge here. It's also not Delaunay, so you flip it. Then you check with the one on the left. It is Delaunay. The disk is empty. You don't do anything. And potentially, you would propagate flips until for each new edge that you create, and you flip until everything is OK. So you see that at each step, you mix. You first do a check, a geometric check of whether the point lies in a disk or not. And at the same time, you already flip. And then you do the same with the other edge. So you mix calls to the geometric operations and the combinatorics. So the code is harder to maintain. It's less clean, less well separated. And so this was what was used at the beginning, but progressively we moved to the other algorithm for really practical reasons. So a few just details about the actual data structure that is behind. We actually store triangulation of the sphere. We compactify the Euclidean space by adding a vertex at infinity. But this vertex is just to make the data structure clean. It has no coordinates, so we don't do dirty things with approximate coordinates or whatever. We don't have large coordinates. It just doesn't have coordinates. It's a virtual point at infinity. And so even maybe more important is the robustness. So we will never compute the center for the Delaunay triangulation, for making decisions. We never compute centers or radii because they would have rounding errors or whatever. So we compute directly the predicates as signs of polynomial expressions. So if you assume that the input points are rational, so you have signs of polynomial expressions on rationals. And in this way, you can use the exact geometric computation paradigm, meaning that you don't use exact arithmetics because it would be too slow, but you combine exact arithmetics with filtering techniques to ensure that the predicates and thus the decisions are always exact. It's always correct. And the idea behind the filtering is that in practice, the easy cases are more frequent, meaning usually points are not collinear or 4 points are not co-circular. Okay, in most cases, and they are not close to even those degenerate cases. So in general, you know that approximate computations would work, but not always. And so the filtering consists in computing an approximate evaluation of the polynomial expression. And you also compute an error, a bound on the error that you make. And then you check whether the interval of possible values contains 0. If it does not contain 0, then you know that you are either positive or negative, but there is no doubt. And so you know that the sign of the expression that you're looking for is the same as the sign of the approximation. And only in the cases where the interval contains 0, you're not sure, and then you run exact computation with another library for exact precision arithmetic. So you combine efficiency and exactness in this way. So this is the general idea, and we also handle degenerate cases, like in particular points lying on the same sphere or the same circle in 2D. And for this, we use only symbolic perturbations, never anything, and we control, and we have a perturbation that is specific to Delaunay thing and the in-sphere predicate, but is easy to code and works very well in practice. So everything is handled, so normally it always works. And there are a few tricks to improve the efficiency, but I won't say anything here about that. Then I switch to other spaces. So first, the hyperbolic plane. So here I'm drawing everything in the Poincaré disk model, in which the hyperbolic plane is the interior of the unit disk in the complex space, for instance. And the main property that we are using is that actually hyperbolic circles are the same as Euclidean circles, but their center is not at the same place. But since we are only using circles and in-circle predicates, we are not computing coordinates. So actually, the combinatorics of the Euclidean Delaunay triangulation gives the combinatorics of the hyperbolic triangulation. So you don't have much to do. The only thing is that you can have Euclidean circles that are not really hyperbolic circles, are not compact. So what we do, in fact, is that we filter those triangles out. So we have a class for hyperbolic Delaunay triangulations that just inherits from the Euclidean class. And then we remove all the triangles for which the circle would be non-compact. But okay, just there's nothing very hard in that. So this is in CGAL. Then I switched to a bit more tricky things to implement in practice, the case of surfaces. And so first, a few definitions, notation. So we restrict to closed-oriented surfaces. So in genus 1, it's a flat torus that can be seen as the quotient of the Euclidean plane under the action of a group given by two translations. And in higher genus, those surfaces are actually hyperbolic, and they can be seen as the quotient of the hyperbolic plane under the action of a group. So this time, it's also a group of translations, but hyperbolic translations. So it's a Fuchsian group. And it's a group of orientation-preserving isometries in the hyperbolic plane. It's isometric to the fundamental group of the surface. So one important property is that this group, those isometries don't commute. So this is a major difference compared to what happens in the Euclidean case. So again, for pictures, I will use the Poincaré disk model. Oops. So the universal covering space in the genus 1 in the flat torus is the Euclidean plane, and in the case of the hyperbolic surface, it's the hyperbolic plane. And I denote as pi the projection from the universal covering space to the surface. So this is for notation. So with pictures, so the flat torus, you can see it. So the universal covering space is tiled by a small tile that is a parallelogram, generally speaking. And so you have infinitely many tiles. And you can see the torus as what you get if you identify opposite sides of the tile. And how we see the Delaunay triangulation in this case. So if you go to the universal covering space, you have infinitely many points given by a few points and their orbits under the group of translation. So you get a triangulation. So it is Delaunay if all triangles have an empty disk here, as in the Euclidean plane. So each triangle has infinitely many images under the group. And what we actually want to compute is one triangle for one representative for each triangle and adjacency relations. So here, this triangle will be adjacent to this one in the data structure. So you do that, and all triangles have a neighbor on the other side of the square. So this is for definitions, and in fact, we started to work on that many years ago in 3D, in fact, because it was requested by some CGAL users. And so in particular, people in astrophysics, for them, it was a way to model what they call the cosmic web. And so they have a probabilistic model that says that if you take any cube, you must, it has the same properties than the cosmic web itself. And since you have so many things, you restrict to a cube to compute the properties. And in fact, the cube is still large because you can have 10 million galaxies inside. So, but for us, it's just points. So we don't really care about the scale. And on the other side of the scale, you also have applications in materials. So it's very small. It's really the opposite. But you also have a lot of periodic materials. Okay, so this was an initial motivation. Then I switched to the Bolzan surface. So here the Bolzan surface is the same idea, but we are on the surface of genus. Here it's genus 2. And you can see it as what you obtain if you take a regular octagon and you glue, you pair opposite sides. So you pair the red ones, you get something that looks like a cylinder. And then you pair the blue ones, and it's something that has a handle, but also a boundary here. Then you pair the two green, and you get this. And then you pair finally the two pink, and you close the second handle. So this is a very specific surface, the fact that it is a hyperbolic octagon, regular octagon. So it's very specific surface. And the octagon is also, if you take the point, the origin, and you take its images, its orbit under the group G, so you get infinitely many points. And the octagon is the Dirichlet domain, which is the cell, the Voronoi cell of the origin in the infinite Voronoi diagram of the orbit under the group. Okay, so what is the Delaunay triangulation in this case? So you have points on the surface. So here I draw those points in the universal covering space. So you have those points in the octagon. So you have infinitely many points in the universal covering space given by the orbits under G of all those points. So you have an infinite triangulation. So it is Delaunay if all circumdiscs are empty. So same definition as usual. So each triangle has infinitely many isometric copies. So those two triangles are really isometric. They are the same. And as for the flat case, what we want to compute is one copy for each triangle with adjacency relations that correspond to the group. So this triangle here will be adjacent to this one here. Okay, so that's what we want to compute. So as I said, we like Boyer's algorithm for practical reasons, but it is problematic in the case of a surface. So if I go back to the Euclidean case, I told you that the union of triangles in conflict, those whose circle contains a point, is a topological disk. You can star the region like this. But in the case of a surface, the conflict region can very well turn around the handle. And then you cannot just star, because to go from the new vertex to a point on the boundary, another point, a vertex on the boundary, you have multiple geodesics. So you cannot just do that automatically with a combinatorial operation. So it does not work in the same way, this algorithm. What you can easily prove, I will do that next, is that if you have this condition on a set of points Q, that we call dummy points, then you can ensure that the whole will be a topological disk, even if you insert more points. So if you start with a set of points Q, satisfying this condition, it will still be okay when you add more points, and the algorithm will work. So to define the notation, this delta denotes the diameter. So here I'm in 2D, but okay, it's the diameter of the largest empty disks of the empty disk in the universal cover. And this here is the systole, the length of the shortest non-contractible curve on the surface. So if you have this inequality, then you can just mechanically use Boyer's algorithm. And the proof is really easy. So if your diameter is smaller than half the systole, so you have two empty disks, you put them together, they cannot intersect anywhere else, because the diameter is too small, they cannot join. And so if you have two edges, in such two Delaunay edges, they are contained in some empty disks, they cannot form a cycle. So you have a simplicial complex and everything will work. So the proof is easy to understand. And of course, if you add more points, it will still work, because the spheres the circles can only get smaller. They cannot get larger in a Delaunay triangulation. So it will work. So the idea that we used for the practical algorithm is to start with a set of dummy points, what we call dummy points, a set Q that satisfies the condition. And then we have a simplicial complex in our data structure with adjacency and relations and everything. And so we can insert points. But so we have those dummy points that are left. And so if possible, at the end, we will remove them, because they don't mean anything for user. But so in general, the user will insert millions of points. And in the end, we can remove without any harm the points that we added at the beginning. So that's the idea that we used both for the flat torus, but cubic and square, that's all that we coded so far, and the Boltzmann surface, it's the same idea. But if we want to generalize this to more surfaces, then there are many issues. So first, we don't know how to compute the systole in general. And we don't have a clean algorithm to compute the set of dummy points for a given surface. And even if we had an algorithm in general, you have algebraic numbers in the group, G, the group of isometries. And so it gives rise to high degree algebraic numbers, so we cannot handle them in practice. And we don't even have a general bound for the number of points in the dummy set of points. We have proved a bound on very specific surfaces, like the generalization of the Bolza. So instead of an octagon, you take a 4G gone, a regular polygon in the hyperbolic plane. So it's very, what we can do is really a few surfaces. So there was another idea, instead of computing on the surface, to compute on the lift, on the covering space. But so if you have a set of points in the hyperbolic plane, if you compute Delaunay triangulation, you get a triangulation of the convex hull. If you want really the triangulation of the whole surface, you need to put a few copies, some copies of the input points, some images under the group, to make sure that you have everything you need to get, if you project to the surface, to get the correct triangulation. And this is a real question: how many and how do we choose the copies of the points, the images of the points that we need to put to get the correct triangulation? And so in the plane, in the flat torus, we could prove that we don't need more than 13 if we know a Dirichlet domain, so a Voronoi diagram of 1 point, a Voronoi cell. So only 13 are enough. So this is actually in progress to code this for CGAL. I'm not sure that it will be very efficient, but it should reasonably work. But in the hyperbolic case, the bound that we have is what I showed, 2g to the power of 2g minus 6. So it's huge. It's a huge number. And of course, we are not going to implement it. So it's a theoretical bound, and that's all. So we need to find something else. So actually, we go back to the flip algorithm in that case. So I recall, so you insert the point, you split a triangle, and then you propagate the flips if the edges are not Delaunay edges. What is known for quite a long time is that the flip graph in the plane, in the Euclidean plane, the flip graph of triangulations is connected. And if you have n points, you take any triangulation, you apply a quadratic number of flips in terms of the number of points, and you get the Delaunay triangulation. So this is known. And what we could prove in the hyperbolic case is that the flip graph of geometric triangulations is also connected. And we still have this quadratic number of flips in terms of n, but we have a factor, a function of the genus and the input triangulation, the quality of the triangulation. And so the termination is quite easy to prove. So for instance, in R2, you take, for a triangulation, you measure the weight of the triangulation as the sum on all triangles of the number of points in their open circumscribing disk. So you can count that. Before a flip, you have a certain number. After a flip, you are sure that you have lost at least 2 in the weight. The 2 endpoints of the new edge are not anymore in the open disk. So you are sure that you will terminate, and so the flip graph is connected. And you can actually prove, so this is something I'm not going to do, that the number of flips to get the Delaunay triangulation is something that depends on the group, the 2 translations that generate the group of translations, and the length, the maximum length of an edge in the input triangulation. So it's a term that measures the quality of the input triangulation compared to the final one, to the Delaunay. Okay, so this is for the flat case. For the hyperbolic case, you a priori cannot do the same because disks, as I said, are not always compact, so this weight would be infinite. But we can prove a lemma that says that the edges are shorter than some constant depending on the triangulation. So you have actually something that is compact, and then you can do the same. And so the flip graph is connected. So this term is the diameter of the triangulation. So it's the smallest diameter of a lift, something, the fundamental domain that you get by lifting the triangulation. So you have many ways to lift the triangulation. So the smallest diameter gives you the factor here. So the bound is something that depends on the surface. The C metric depends on S. D of t depends on the quality of the triangulation, and then you have this usual n square. And we believe that this is really overestimated. So we wanted to run some experiments to make sure to see what happens in practice. So I just mentioned that, in fact, this quantity should be L, maximum length of the input triangulation. But okay, as we did the experiments with D, I kept the D, but it can be proved to be L, in fact, which is easier to evaluate. But if you want to experiment, so the main issue maybe is to get input surfaces to test and to run your experiments and get some conclusion. And this is maybe the hardest. So the input should be both relevant, meaning that the input surfaces that you choose should represent everything you can get, more or less. And also, you should be able to compute with that. Otherwise, you're stuck. And this is quite hard. So first, you could wonder whether you can have a set of well-distributed surfaces among the set of all possible surfaces. So the set of all possible surfaces is a modular space. And it's, in fact, the quotient of the Teichmüller space under the mapping class group that are non-trivial homeomorphic of homeomorphisms of the topological sphere. Okay, so is there a hope to be able to get something that is well distributed in MG? This is the one we are interested in. And in fact, we don't know how to do that. There are known parameterizations for T, the Teichmüller space, either by Fenchel-Nielsen coordinates, meaning the things you get by cutting your surface into pairs of pens, or something that is closer to what we did so far is a fundamental polygon and side pairings that give you a group. And but you have known parameterizations for T, but they are not invariant under homeomorphisms. So this does not give you a good parameterization of M. And but that's the best we can do. So, okay, so we stay with the Teichmüller space, but we know that it's not a good sampling, but we don't have a better way so far. Another remark is that Mirzakhani showed that in general, if you take a random surface, it has a large systole. It's not too thin. Okay, that's just a remark about the shape of the surfaces that we get. Then how can we compute? How can we generate surfaces knowing that? So in genus 2, it was shown that every surface, hyperbolic surface of genus 2 has some fundamental domain that is a symmetric octagon. So the symmetric octagon is given by 3 points, Z0, Z1, Z2. And the other points, knowing the area, and knowing the fact that they are symmetric, you can compute all the other vertices of the octagon. And so the parameters to represent any surface of genus 2 are coordinates of those 6 coordinates of those 3 points, which are in general algebraic numbers. So again, we are stuck. If you want to do this in practice, then you will have a higher and higher degree, and it will fail. And what we could prove is that, in fact, if you restrict those 3 points to rational coordinates, you get a dense subset of all possible surfaces. So every surface of genus 2 is close to a surface with given by rational parameters. And then we are happy because we can compute with rational numbers. And unfortunately, in higher genus, there is no known representation on which you can really compute. So far, we are stuck with genus 2, which is a bit frustrating, but at least we can do things. And so the experiments, what do they say? So this was a theoretical result. And so with this genus 2, we actually observe that the complexity is linear in terms of the diameter. And on the average, it looks like being logarithmic. So it reminds us, like some results by Mark Bell, who was studying similar things, but on topological triangulations. So maybe there is a real link to be found. So it's not completely clear. In any case, the cause for this is under review for CGAL. So we'll have a flips on hyperbolic triangulations, triangulations of surfaces soon in CGAL. So I conclude with open or work in progress. So of course, we would like to run more experiments to have a higher genus. With rational numbers is hopeless probably, but at least have low degree algebraic numbers to still be able to compute. So this is work in progress, open, but hopefully soon closed, I don't know. And what we are working on currently is to compute epsilon nets, so of hyperbolic surfaces. So epsilon nets are sets of points such that every point of S is close enough to a point of the epsilon net, and 2 points of the epsilon net are not too close. And so using those ideas like Shushuk's refinement algorithm to compute meshes of objects in the Euclidean space. So we use the same ideas that we start with the triangulation, and each time that circle is large, we try to cut it, to break it by inserting its circumcenter. So we add more and more points until we have the properties that we want. So here are some pictures obtained. So left with a large value of epsilon, and then if you have a smaller value of epsilon, you have more points. So on the right, it's something like a few thousand points that you get for this value of epsilon. What is also nice is that if you draw, of course, there are many ways to draw the lift in the hyperbolic plane, but if you draw it in a way that you make sure that everything is as close as possible to the origin, then in fact the picture shows that you get it's just a picture, but you get a representation of the surface that really looks like the Dirichlet domain. So if you compute the Dirichlet domain, you put the picture, it's really close. So this is more or less available on GitHub, not a public yet, but it will soon be public. Oh, yes, it is public, but not advertised. And so the idea, the motivation for those epsilon nets would be to be able to compute at least approximations of some values that we are not able to compute exactly. So like the systole, I mentioned the systole, the diameter is also something that we cannot compute exactly so far. So having a good approximation by an epsilon net should allow us to compute approximate values for those parameters on the surface. And yes, and that's it. So I think I'm just in time. So
thank you very much. Thank you very much for the talk. Before we go to questions, I would like to ask you to unmute yourself and give a round of applause to Monique.
Thank you.
All right, it's time for questions. So if you have a question, please just unmute yourselves and ask. Or if you can also type it in the chat, or you can raise your hand and I will keep an eye on the chat. Keep an eye on the raised hands, let's say.
So yes, I think, yes, with my background, it's hard to see, but so my my current co-author, Vincent, is with us, so we can share questions.
You
have been there all the time. And we didn't know.
Yes.
Hidden behind.
Hidden.
I'll start with the question, Monique. So I was curious if you could explain this result in the flat torus, how you only need to look at, was it 13 sort of nearby fundamental domain? So any explanations where that 13 is coming from?
For the 13, I'm not sure that I have a good thing, but at least it's this picture. So you have the central Dirichlet domain. You have all the neighbors. So this is 6. And then you have those in the corner. They are not complete. We don't need them all, but still, you would put them also, the neighbors in the corners here. And if you can't, hopefully it's 13. But I mean, there's no miracle. It's just that we have this condition. So
Yeah.
the approach with the dummy points was to reduce this delta. And more or less the approach with, it's more or less dual. The approach with copies of points is to increase, not really the systole because we don't have a surface anymore, but to increase still the size of the domain, to have the similar inequality. So if you have an inequality, to make it valid, you either decrease the small term or you increase the upper bound and you manage.
And so you know which 13 copies to look at as well. Like you know
Yes,
which
because it's really this picture. And we have something, even in 3D, we have a bound that I forgot, but we have a construction. So it's really constructive. So we can really, and this is really in progress. The implementation is really in progress. It's really something, because currently we only have cubes and squares in CGAL. So we would like to have, users have requested slanted domains, thin domains, and they're really.
I see where the fundamental domain can be a parallelogram or something.
Yes, and a very thin one, the bad one. And so you first do a lattice reduction to get a better thing, and then you need the Dirichlet domain. You compute the Dirichlet domain, and you know which copies to consider. And this is really something that. So I am not. My hands are not on the keyboard to implement that, but it's really in progress.
Fantastic! Thanks so much.
Okay, who has the next question?
I'll be greedy and ask another question. So would this also allow one to compute alpha complexes on the torus? Like how many domains do you need to look at to compute the alpha complex? Do you think it's the same answer?
I've not thought about that, but at least I think that the same, but I'm not sure the same answer will work, but at least I think that the same method would allow you to give a bound, I imagine, because it's really, there's nothing mysterious, really, in this work. It was more, actually, it was really more a practical paper. So the proof, but there is a proof in it, but nothing sophisticated. And
Sure, but it's important to figure out as opposed to just
sure.
making copies until things seem to stop changing.
So I guess that yes, looking at the same steps would give you an answer. If not the same, at least it will give you an answer. I've not thought about it.
Fantastic, thank you.
Yeah, I think I actually might have an answer to that, because my former colleague Georg Osang, who is cited here on your slides, I think he did this research because he was interested in alpha complexes. And I think it's really just the same thing, right? Because once you have the Delaunay triangulation, you know where the empty circumcircles are. And then if you want to have alpha complexes, you just compute the radius of those circles. So,
yes. Georg joined. So I did not know that you knew him, but he joined because as a user, he would have liked to have that in CGAL. And since each time some user was asking, my only answer was, I have no time to do everything. And so he said, okay, I need it. Let's work together. And we finally had an answer. But it was really motivation by his user. So that's also something nice about CGAL is that, okay, we have users. And sometimes they're really asking research questions, not just basic use questions on the manual or whatever, but really research questions that are interesting. So that this work globally is really a good example of that because of the astrophysicists and also Georg and it's really interesting to code in CGAL at least be only for that. To have newer research questions, things that I would not have thought about. I mean,
I'll ask another question. So you discuss triangulations on these surfaces, you know, these negatively curved surfaces. Does positive curvature come up, or would that require too high of dimensions for things to really be computable?
I'm not sure I get the question. So we also have triangulations on the sphere. But I mean, triangulations on the sphere, you think a bit step. It's just a convex hull. So it's rewarding things, and we can reward them. And in fact, we have a nice piece of code that goes incredibly fast. But okay, this is a positively curved surface, the sphere. But it's just a convex hull, in fact. And the code works well, but and for other surfaces, maybe you have something to say.
If you want to do Delaunay triangulation on random Riemannian surfaces, for instance, it becomes a lot more complicated because you have to store your metric somehow, and this is hard. You have a paper by Jean-Daniel Boissonnat, and I don't.
Yes, but then yes, our approach is to is to put. I mean, it's a different issue. It's kind of a different problem because they prove the things on Delaunay triangulations on some Riemannian surfaces, but to prove things they put many points so that the approximation is good enough. And so it's really a different issue. It's not given a set of points, compute the Delaunay triangulation. I think that nobody does that on generic.
No, because I don't see a thing to have a combinatorial representation of general Riemannian surface. You can have very compact representation for a hyperbolic surface with a little number of parameters, which is not possible in general.
Yes. This is completely open for practical things. We are very far from that.
But we
I remember being surprised. I think I saw this paper. I'll get it wrong, but roughly it was saying that even if your sample is arbitrarily dense on a Riemannian manifold, the Delaunay triangulation isn't necessarily a triangulation. You need some epsilon separation properties as well, if I remember correctly.
I forgot the results. It's a paper by Jean-Daniel Boissonnat, Ramsey Dyer, and probably somebody else. And they have something about surfaces, Riemannian surfaces, and triangulations, Delaunay triangulations, but it's it's completely different approach.
And you need to have a sampling in the beginning that is dense enough with respect to some specific parameters of the surface, so it's difficult to.
There really many points. To be able to prove something.
Thanks so much.
Are there any more questions? I was wondering, you were saying that, like at the end of the talk, you were talking about sort of adding points by inserting certain circumcenters, sorry.
Circumcenter, yeah.
But you were also saying at the beginning of the talk, if I don't get it wrong, that calculating the positions of the circumcenters is difficult in the hyperbolic case,
Yeah,
at least in the hyperbolic case.
You don't want to compute with algebraic numbers again, and but in fact we don't care whether it's really the circumcenter or not. What we want is to insert a point that breaks the triangle, and so we insert something that is close, an approximation of the circle, and that's good enough. The only thing is that if you really want to make sure that it's an epsilon covering and an epsilon packing, if you compute approximations, you lose the guarantee of the distances. So what we actually do is that, so we do things with approximate circumcenters, and in the end, we do a net that check to make sure that what we have computed is actually correct. And on all the surfaces with a systole that is large enough, it really works experimentally. In the end, we always have an epsilon packing and covering. It's just on, we tested, so they are hard to generate, but we could force one surface with a small systole, a very small systole, and then in that case, it did not work, which shows that we would need more complicated arithmetic. We cannot just play with rational numbers. If the surface is too thin, it's not going to. But as yes, most surfaces have a large systole, which is that's the best we can do so far.
Yeah, and additionally, the fact that we construct points makes the insertion a lot longer in practice.
Yeah. It's less efficient because yes, we don't rely on predicates only. We really construct things. But the question is different. So
yeah, but if you start to see some time of computation around 10 million points on the Bolzano surface.
Yeah, it's not the case here.
Yeah, it's more like 100,000. It's already in an instant. So
yeah. And also, but I cheated a bit. I cannot say everything, but I presented the data structure at the beginning with cells and adjacent cells, and this is really not what we use here. And for hyperbolic surfaces, we use combinatorial maps, and we store, in fact, the cross ratios on each edge. So it means that each time we update the triangulation, we need to compute cross ratios. And this is really construction. Again, it's not a predicate. It's completely the operations that are done are really different. So, not say everything, but yes. So everything that I said on the Euclidean or even flat case does not apply here. What we do for generic for Bolzano surfaces, it also worked because there are algebraic numbers on the Bolzano surface which we handle, but they are relatively low degree. The predicates are less than 48, if I remember correctly. I'm not sure, but we have a bound on the degree of algebraic numbers that we need to handle. Whereas if you take a generic surface, a priori, you don't have, we don't know, it depends on the isometries and everything. And it would be complicated. So here we approximate with rational numbers, and we only insert rational circumcenters. But still, we have constructions. So it's completely different. But there is hope to be able to do things still.
Yeah. But if you have the epsilon, and so you have the problem with the small systole, which I get. But if epsilon is much smaller than the systole, isn't it kind of I don't know, because like the problem with the hyperbolic surfaces is that you can't just you can't scale them, right?
Yeah.
So you would think like, oh, just scale it and you're back to the original, but it just doesn't work at all.
I mean, if the what we're trying to do, if the epsilon is larger than the systole, then at some point in the triangulation, you will have a loop.
Yeah.
And so we're trying to cut the cylinders around the systole to separate the thin part from the rest.
And that would be promising also in terms of, I mean, I cannot imagine how one would
at least in theory. We haven't tried to implement anything with that, but at least the paper is not completely written, but we believe that it will work in theory, but in practice,
yeah, it's pretty fine in theory, but you have some computation of length at some point. And there's some hyperbolic tangent and stuff like that.
Hyperbolic trigonometry
and,
is an issue in practice.
Yeah.
So in theory, yes, you can do things, but
yeah, because if you have a small systole, then it has a long collar, and it means that your Dirichlet domain, for instance, will be very close to the boundary of the disk. And then if you're too close to the boundary, you start to have strong problems.
Arithmetic numbers, because the points are too close and no, we are not going to have that in CGAL tomorrow. It's not going to happen.
But by Christmas, maybe, I don't know.
Okay, you can believe in Father Christmas, but
yeah, in Christmas in 2030 maybe.
Some Christmas, yes.
Okay, thank you.
There are nice questions, funny questions, hard but interesting. Nice questions.
Is there anybody else who would like to ask a question? Okay, well, if that's not the case, then thank you again for the great talk and also for the discussion at the end.
Thank you very much.
I'll stop the recording now.
Also the discussion.